Welcome to a lesson with Dr. Powell. Let's take a look at the gluing diagram for a torus, or in other words, a donut. Okay, there's many different gluing diagrams you can do, different cell complex type structures. This is just one I've chosen just so we can look at matrices for these and think about kind of what we get with Smith normal form. So, taking a look at this, let's think about this for a minute. Now, how is this a donut, first of all? So, see these arrows here? They kind of glue together. That would make so kind of think of this wrapping around and kind of lining up those arrows together. So it kind of makes a tube, a funnel like this. And then B would be wrapped around down here, B right here. And as you bring them down around together, it encloses it. So you end up getting a donut. Okay. Like that. So we get so this is can be thought of as a gluing diagram for a donut or a torus, and let's see what kind of information we get from it. The map, the boundary one map, so from edges to vertices, that's going to let's think about this. How many vertices do we have? There's only one vertex total. Completely, and it looks like that every edge kind of has a v. Oh my goodness, it goes to v minus v. It goes to 0. And so if we were to think about this, we have three different edges coming in, A, B, and C, and they're all going to end up going to 0. I mean, that's partial one. It tells us something. I mean, it tells us that the actually, and partial one is already in Smith normal form, 0, 3, 0 columns, and the kernel is going to be dimension 3. I mean, it's going to be the whole thing, all of E. So actually, E itself is equal to the kernel of partial 1. Okay, so we got that. Now let's take a look at the matrix for partial 2, or the boundary map 2, boundary 2. So we think about this, the different faces coming in. We have face 1 coming in, face 2 coming in, and we'll note too, this is A, B, and C. So face 1 has A, so A, B, and then negative C, right? So we have, so here we have A is positive B, and then a negative C, and F2, going to positive C minus, okay, so it looks like um, right. So for this one, we have C. Okay, so we have a positive C, then we have a minus minus. Okay, so that's the partial 2 map for this particular one. That's the partial 1. Now, the Smith normal form of this guy, if we take a look at that, we'll just think of these two columns are just multiples of each other. So really, in the end, I mean, this can easily zero this guy out, and then you can use 1, 0 on the top to zero out what's below it. So we really get just a 1 in the corner. And what does that tell us? That tells us that the range is just 1. A dimension has dimension 1. Okay, the range of that guy. Okay, so what we have is now noticing or realizing that the range of this guy is inside of the kernel of that guy. We can make a quotient space, this vector space over a subspace of it, the range of the range of this boundary map. So the kernel, that guy, and we mod out by the range of this function here, this boundary function, and we look at the dimension of that. Now, noticing at least with vector space dimensions, things just subtract. So this kernel dimension, what is it? It's dimension 3, and this dimension right here is dimension 1. So the dimension of the quotient space, just subtract the dimensions, 3 minus 1. What's that? The dimension of the quotient is simply equal to 2. How can we interpret that? Well, the kernel is just simply loops. Well, everything in here will, at least in this case, is a enclosed loop. So you have a enclosed loop on our surface. So there's lots of enclosed loops, and when we mod out by this, we're modding out by boundary information, like all all ways of making, in fact, whenever you have a boundary, it's kind of like all ways of making two paths the same path. So a path right here, if you mod out, if you make the boundary between it like 0, it actually compresses and makes these two edges be the same edge. So really, it's kind of a collapsing mechanism. It collapses things. And this quotient is actually the same no matter which gluing diagram we used for the particular object at hand. So even if we included a lot of faces, we still get the same thing. So really, this mechanism works across, even taking a limit, across all edges and loops and things that we could get. So really what we're saying here with dimension 2, we're saying that there's two distinct at least but remember this is with as vector spaces. The dimension of the classes of loops, I should say, is 2. Okay, of distinct loops. So we have to have a basis of 2, guys, and what would they be? 2 linearly independent loops. Well, if you think about it, if you have a donut, you can kind of imagine this. Okay, we have a loop going this way, and you also have a loop kind of going around just right here. Notice that, and maybe they both emanate from this point. Notice a loop going around, like in back, and then around and then just right here in front. So this loop right here goes like inside the donut hole, around on the other side, and then goes back around. So both of these loops are distinct and linearly independent. They can't morph into each other. And that's what this is saying. And then what you could do is you could go this way, then you could go that way again and wrap around lots and lots of times that way. And then you go this way and wrap around lots and lots and lots and lots of times that way. And every time you wrap around, that's kind of like another scale. It's like adding to the scalar coefficient of what we're working with. Now, albeit we're doing vector spaces right here, so we could have real numbers and we could rescale it in different ways. It's not as great as thinking about it if we were working over just with scalars in Z. However, just for simplicity with our matrices and Smith-Normal form and other things like that, working with just the real numbers here, we're just kind of keeping things simple. We at least kind of get a feel or sense for what might be happening. This dimension of 2 tells us kind of, in a sense, for how loops or how strings or knots or whatever you can get around on the surface of that have to stay on the surface of the donut, kind of how they behave, and it gives us a sense or feel of how to classify this surface as being distinct from that of a sphere. Thanks for watching.